Hi all, and thanks for joining this webinar. My name is Rohan, and today we'll talk about end-to-end development and testing of controllers for robots and autonomous systems. So let's get started. Robots and autonomous systems can generally be categorized based on their intended use, functionality, and environment. Today, we will be focusing on robots and autonomous systems for industrial and service applications. Industrial robots are typically used in manufacturing and production environments optimized for precision, repeatability, and real-time efficiency. Examples include assembly lines for manufacturing cars and delicate parts like circuit boards. Service robots are robots to assist people by performing tasks that require flexibility, mobility, and real-time decision making. The examples here include robot-assisted surgery and rehabilitation devices, and autonomous systems for delivery, agriculture, hospitality, and humanoid robots. Developing and testing the controllers for these robots and autonomous systems is crucial. Innovative control design ensures that the robot or autonomous system can respond accurately to its environment and make real-time decisions. This is where real-time testing of the controllers becomes important. Why so? Let us see one such example. The robot here is designed for tasks like inspection, data collection, and navigating through challenging rocky terrains or debris-filled environments, which require real-time adjustments to its control algorithms. By testing the controllers early in your development journey, engineers can identify and address potential issues such as balance problems, sensor miscalibration, or response delays before deployment. This tells you why real-time testing of controllers is essential. So let's get back to the plant controller system to discuss the base architecture of such robotic systems. Most generally speaking, robotic systems consist of a controller and a plant. An input signal is applied to the controller, which controls the signal fed to the plant, and in a closed-loop system, the output is connected back to the input. The controller could be for an industrial robot, a robot prosthesis, or even an unmanned aerial vehicle. During development, you can use the SpeedCode real-time target machine as a prototype controller and refine your algorithm controlling the real system. This is called rapid control prototyping. In a later step, you want to test your embedded controller extensively in realistic scenarios. You can do this by connecting it to the SpeedCode target machine working as a hill simulator running a digital twin of the plant. This allows you to test earlier, automate your tests, and cover edge cases which would be dangerous using the real plant. The controller development solution by Mathox and SpeedCode is designed to assist you with technical and workflow challenges. Benefit from a fully Simulink integrated solution that provides flexible and automated workflows for prototyping and testing. Powerful software and hardware solutions for developing the complex control systems of robots and autonomous systems, and modular test systems that can scale with your needs. SpeedCode test systems are equipped with key I/O modules which include fast and high-resolution analog and digital I/O modules, and protocol support for CAN, EtherCAT, Modbus, UDP, SPI, I2C, and vision protocols such as Gigabit Ethernet, USB UVC. The SpeedCode and Simulink ecosystem also provides support for middleware, which is a collection of libraries and tools that help developers create robot control systems. This includes ROS and especially ROS2, which are better for real-time controls, security, scalability, and robust distributed systems. There's also DDS, which helps ensure reliable, low-latency communication between robot controllers and sensors. SpeedCode and Simulink model-based design for robots and autonomous systems ensure that the requirements can be traced to models and the code automatically generated and the tests needed to fulfill verification and validation tasks. Let us now look at the industry trends for robots and autonomous systems. Engineers today are using model-based design approaches with Simulink and SpeedCode from control design prototyping to controller testing end-to-end. They're increasingly using AI and machine learning to enhance their perception and decision making with autonomy, unlike traditional robots which rely on pre-programmed instructions. They're using edge computing for low latency real time processing. They're testing the controllers using high fidelity digital twins, which help replicate real world behaviors and dynamics of the robots and autonomous systems. They're using digital twins to certify and virtually commission the controllers of the robots. Before we dive further into our solutions, now let's review today's webinar agenda. First, we'll introduce typical workflows and key capabilities of the solution. We will then shift the focus towards dedicated solutions for control systems of robots and autonomous systems with 3 hands-on demos leveraging Simulink and SpeedGoat test systems. We will see how they can be used to prototype and test controllers for unmanned aerial vehicles. And finally, we will wrap up with some key takeaways. So let's get started with the key workflows and capabilities. As said before, engineers are using model-based design approaches to prototype, control designs, and test the controllers. Using Simulink and SpeedGoat, you can test your controllers end-to-end, from requirements to validation and deployment. Under control design prototyping, you design the controls on Simulink, deploy to the SpeedGoat test system, which acts as a controller prototype for the robot. For hardware-in-the-loop testing, you create robot models in Simulink and deploy to the SpeedGoat test system, which acts as a digital twin of the robot to test the controller. Simulink provides the robotic systems toolbox, which provides customizable templates and pre-built models for robots, along with motion planning, trajectory generation, and other scenarios to simulate. You will see these two workflows in action in the upcoming web demos during the webinar. The integration of artificial intelligence and machine learning into the robots is enabling them to adapt, learn from data, and make decisions in real time. MathWorks provides the reinforcement learning toolbox, which allows the control design prototype to learn optimal behaviors through interactions with the environment and tune the parameters based on the feedback received. It is ideal for training robots to perform tasks like path planning, robotic manipulation, and other autonomous applications. Apart from this, MathWorks also has a deep learning toolbox, which provides functions, apps, and Simulink blocks for designing, implementing, and simulating deep neural networks. The toolbox lets you interoperate with other deep learning frameworks such as importing PyTorch, TensorFlow, and ONNX models. Processing such deep learning networks in real time requires data processing at high sample rates. For this, SpeedGoat provides Simulink programmable FPGAs, which process the signals in the megahertz range on the test system. These high-speed FPGAs allow for performing computations directly on the control design prototype of the robot instead of relying on distant cloud infrastructures. For robots with computer vision applications, there is a dedicated Vision I/O module that can acquire camera image data, emulate camera protocols such as Gigabit Ethernet, USB UVC, and can process vision data and control algorithms, including deep learning algorithms. Testing the controllers for real robots and autonomous systems can be cumbersome, and it is not possible to safely test all scenarios. Hence, creating a digital twin of the robot helps accurately test these controllers safely. Along with this, the SpeedGoat MathWorks ecosystem allows you to seamlessly connect with simulation environments such as Unreal Engine, Unity, NVIDIA Isaac Sim, and Gazebo. The high-fidelity simulators allow engineers to model complex environments and robotic behaviors, optimizing design and functionality. For the certification of robot control systems, we have to ensure that it complies with industry-specific regulations, standard, and safety protocols. The MathWorks SpeedGoat ecosystem provides toolboxes for certification standards such as IEC 61508 for functional safety for industrial applications, IEC 62304 for medical device controller development, IEC 61511 for functional safety of safety instrumented systems used in process industries, DO 178C for software considerations in airborne systems and equipment certifications such as for unmanned aerial vehicles, ISO 26262 for functional safety for autonomous applications. Let us now look closer into the hardware and integration benefits. The performance machine is the most scalable and performant system with highest I/O flexibility. It is the mainstay for hardware-in-the-loop testing, or HIL testing for short, which can be used to complete verification and validation activities. The mobile, baseline, and unit machines are smaller and rugged, making them suitable for applications requiring more portability and fewer I/O channels. Let us now move to dedicated solutions for robots and autonomous systems. The first demo is of a control design prototype for a robot arm. But before that, let's look at a workflow needed before you even start working on your control design prototype. When starting real-time testing, you often need to integrate new components like sensors and actuators and set up the required interfaces. More specifically, we will connect to an inertial sensor, perform spontaneous real-time measurements and data pre-processing. We are using a 9-axis inertial sensor which communicates over an I2C protocol, a common serial interface. To set up and test the sensor, we use a SpeedGoat unit real-time test system. So let us switch to MATLAB and Simulink to see how this works. In the Simulink model, you can see on the left side the subsystem where we take the sensor readings from the IMU. To communicate with the sensor, we are using the IO397 configurable IO module. Configurable means that it can be easily reprogrammed with configuration files that enable different functionalities, such as the I2C interface, which we will be using here. For communication, we need the device ID and register addresses to read from or write to. We set up 2 write signals here to configure the sensor, and then we want to continuously read out 14 bytes of data containing the accelerometer, temperature, and gyroscope data. We have already selected these output signals for logging to the simulation data inspector. To log additional signals, just click on it and choose Log Selected Signal, and our model is already configured for real-time execution. But for any other Simulink model, you could simply go to the Apps toolstrip and select Simulink Real-Time to adjust the needed settings. Namely, this will configure the model to use a fixed step solver and generate code for Simulink real-time targets. Directly from the Simulink toolstrip, we can now click Run on Target, which will compile, deploy, and run the model on the SpeedGoat real-time target machine. While the model is running in real time, we can observe the logged signals in the simulation data inspector and verify that we are in fact getting sensor data and the signals reflect the movement of the sensor. Aside from the simulation data inspector, you can also use specific Simulink blocks to analyze the signals like a scope or a spectrum analyzer. Similar to simulation data inspector, these blocks allow us to visualize the data where the model is running. The scope has many functionalities similar to an oscilloscope like cursor measurements, bi-level measurements, or triggering. The spectrum analyzer could be useful, for example, to analyze the noise in our IMU signals and design a filter to improve the signal-to-noise ratio. We hope this illustrates how quickly you can run your models on SpeedGoat Target directly from Simulink, connect with sensors and other hardware using the SpeedGoat IO block set. Let us now continue with the control design prototyping demo for a robot arm. We have here a robot arm with 6 degrees of freedom. We design the controls on Simulink and deploy to the unit real-time target machine acting as a prototype controller. This prototype controller communicates with the robot arm using the EtherCAT interface. The robot arm is used to provide a touch on the cell phone in a particular pattern. This feedback is used to test and optimize the control design. Let's start with a brief look at the Simulink model. We have some push buttons and indicators for testing the robot right from Simulink, then some input and output interfaces which use the EtherCAT protocol to communicate with the robot, and finally our main controller which is implemented in Stateflow. But what we want to focus on now is the user interface built with the MATLAB App Designer. Here you can see the App Designer window and the app that we have created so far. This is the design view where we see a graphical preview of our user interface, which we can modify with just drag and drop. There is a UI axis plot where we will display the phone screen image, and then we have some buttons and status lamps to interact with the robot. Of course, we need to code what is going to happen when each button is pushed, So this is done using callback functions. We can jump to the callback function by right-clicking the UI element and select the callback, which will switch over to the code view. The grayed out parts of the code are automatically created when you add an element in the design view, and we only need to add the core functionalities. Here, we are setting some parameters on the target machine using the setParam command. Similar for the lamp indicators, we have functions to set the color based on status changes. What's still missing though are some buttons to interact with the target machine itself. What we see here in the app designer are their pre-built buttons for Simulink real time. These require no coding at all, taking a lot of work off your shoulders. We will need now a drop-down menu to select the target machine and a start button, of course. And before we can start, we also need to connect to the target machine. And finally, it's always a good idea to have some status indicators. And as said, these buttons work without any additional coding. But sometimes you still want to add some additional functionalities. And in that case, you can still add another callback function. App Designer then creates the function stub, and you can simply add everything else you need the function to do. When we are ready to test our app, just click the Run button and the App Designer will compile and start your app. So now, let's see our robotic touch device tester in action. On the left side, you can see a screen capture of the MATLAB app that we just showed you, and on the right, a camera view of the robot. We only have to click a few buttons now, and the robot will do all of the work for us. First, we start the real-time application on the target computer, and the robot will automatically perform a homing movement. Then, we proceed with telling the robot to unlock the test phone with factory default pin code. Afterwards, we select to open the test menu, which is done by entering a standardized sequence in the dial screen. And finally, we run our test function, which will start and execute the touchscreen test. On the direct video feed from the phone, we can clearly observe if all the checkboxes turn green. This check could of course also be automized in a later step using image processing. With the test successfully completed, the phone goes back to the test menu. Before we move to the next demo, let's check out a customer story from the Soft and Micro Robotics Laboratory at MIT. The researchers here are using artificial muscles to power insect-like aerial microrobots. As the size of these robots shrinks, the dynamics becomes faster, therefore requiring higher sensing and control rates. With 400 wing flaps per second, the feedback control needs to run at 10 kHz frequency. The researchers model and simulate the dynamics at different fidelity levels to identify the optimal wing shape. Various experiments are performed to identify the mapping from actuator inputs to lift, resulting in an accurate flight dynamics model. This is then used to test new control designs in closed loop without the risk of damaging the real robot. And finally, the control design is deployed to the SpeedGoat test system as a control design prototype to test again with a real robot and sending the actuator command back to the robots. That was an insight into the development of complex control systems using the SpeedGoat test system as a control design prototype. Now, let us go back to the same robot arm, but now we will show you how to prototype the control design with a camera incorporated to get vision data. Let us imagine a scenario where you develop a robot with computer vision capabilities. Here, we use the same robotic arm as in the previous demo and modify it to be a vision-guided multiple degrees of freedom arm that can sort between some physiological markers labeled red and blue. In the simplified scenario, inspection of the markers is done using images from a gigabit Ethernet camera, and the computer vision algorithms then enable detection. The SpeedGoat Performance real-time test system will handle this task as well as generate movement commands for the robot to pick and remove the respective paths. The communication interfaces in this example are the gigabit Ethernet for camera input and the EtherCAT, a widely used industrial protocol to control the robot arm. Note that the performance real-time test system is equipped with a Simulink programmable vision I/O module. This takes care of the challenge of processing high resolution video in real time, which requires a lot of processing power. This is a hardware setup for testing. As placeholder for physiological markers, we are simply using differently colored balls, where the red ones represent the physiological markers that need to be removed. The camera is mounted in a fixed angle overhead and the opposite side of the robot. Let's first see how the computer vision algorithm works on a very high level. The overhead camera image is cropped to the area of interest, and thresholding is done on an intensity image, which is used to remove the background. An algorithm for connected component analysis, or CCA for short, then calculates the bounding boxes and center coordinates for each object, and we filter them by primary color to detect the red balls. Finally, we transform the detections from pixel coordinates in the robot's reference frame and send them down the data stream. The object detections are then fed into the supervisory controller for the robot arm as planar X and Y coordinates. The move commands generated by the controller are sent to the robot using EtherCAT transmit blocks from the Simulink Speedcode iBlock set. We won't get into the details of the inner workings of the controls, but it basically consists of a state machine which goes through all the necessary initialization steps. It then keeps the robot in a neutral position until we trigger it to pick up an object. Once we do that, a trajectory auto object is generated and the robot moves to pick it up and puts it in a container to the side. We have also added two dashboard indicators to observe the state of the system and a trigger button. We are already connected to the real-time target machine, as we can see in the top left corner of the Simulink tool strip. So, we just click Run on Target and the model is compiled, loaded, and executed on the target. You can see that the robot on camera here and the dashboard shows that it is initialized and the objects have been detected. So, when we click the pick button, the robot will move to the first object from the list and remove it. We simply click the button again while objects are still being detected. Of course, this could be fully automated later, but for testing, it is handy to have these controls. Continuing further, let's also discuss a little about the Speedcode system as embedded controller for your prototypes. You may ask why? So first, you get the closest connection possible to Simulink to implement controller changes. Second, you have less or no constraint on your compute resources, especially when you're trying different controls concepts. Third, the Speedcode system ensures deterministic real-time behavior of a controller, which a desktop environment can hardly provide. Overall, it is not only great for testing and verification and validation, but also leads to reduced costs and risks and shorter time to market. So before we get into our next demo, let us look at a customer success story from Humotech, who are developing solution in the space of robotic prosthesis. Their Caplex system is a prosthetic emulation platform with control hardware that integrates the Speedcode baseline test system, processing sensor and actuator data from wearable devices. Let's hear from Humotech CEO, Dr. Josh Caputo, on this collaboration with Speedcode.
Hi, I'm Josh Caputo, founder and CEO of Humotech. We're a Pittsburgh-based company spun out of Carnegie Mellon University. We're dedicated to transforming the way the world develops and uses wearable machines, including prosthetics, exoskeletons, and beyond. Our current business is focused on providing the innovators in this space with all of the necessary hardware and software tools they need to develop and test control algorithms for these systems without having to do any reinventing of the wheel. At the heart of our work is what we call the Caplex system, a modular, customizable, and scalable platform that's supporting a broad range of research and development. From deepening our understanding of human biomechanics to supporting the development of new product ideas or informing potential new advanced rehabilitation strategies. Designing control systems for these kinds of systems is challenging, so we've developed our tools to make this easier, faster, and we've really strived to lower barriers to access. Real-time control is crucial because of the human safety aspects, as is performance because human biomechanics requires high loads and fast motion. Controllers must be both stable and intuitive to use. The robotic system must be helpful when assistance is needed and transparent when it's not. Our solutions rely on model based design with Simulink deployed to SpeedGoat hardware. These tools enable us and our customers to hit the ground running. Everything just works with minimal setup. And we've designed an environment in MATLAB Simulink that is very flexible across applications. Our code quickly adapts to low or high numbers of degrees of freedom, prosthesis or exoskeleton assistance, people of different body types, different sensor suites, and so on.
After looking at control design prototyping and implementation of the controllers, you may want to test the controller itself. Using a digital twin of the robot, you can test your controllers safely and can automate the test case execution. In the next demo, we will see how to virtually commission a programmable logic controller of a robot using hardware-in-the-loop testing. But first, let's see how to create a realistic and accurate digital twin model of your real system. When you buy robotic components off the shelf, you typically get the CAD 3D models with it. So we'd like to show you how you can use those for creating a Simscape model. For a few robots, the CAD data is even directly included in the robotic systems toolbox, along with many other 3D models. One simple command loads the data and we can already view a 3D representation of the robot. Using the function smimport, we can then generate a Simscape multibody model from it. Here, we see the generated links and joints, adjust parameters such as inertia and mass distribution, or let MATLAB automatically calculate these values from the part's geometry. When we simulate this model, the Mechanics Explorer shows us a 3D visualization of the scene. This is just a blueprint model with no controller yet, but it can be quickly used to perform kinematic or dynamic simulations and develop motion planning and motor control algorithms. Let us now look at the hardware-in-the-loop testing setup. The PLC that we have chosen here is the Beckhoff EK1110. We have already deployed the control algorithm onto the PLC using the TwinCAT software. In this demo, we will focusing on using hardware-in-the-loop testing to validate this PLC. To enable this, we use a SpeedCode performance test system, which is ideal for hill applications. This is used as a digital twin of the robot and other industrial automation components. The controller signals from the Beckhoff PLC to the SpeedCode test system are sent via the EtherCAT protocol. We now open the Simulink model of the robot arm to be deployed. The robot arm model we have here is that of a KUKA robot, which is widely used in industrial automation machinery. The robot arm has several components such as the pivot, the bicep, and the forearm, among others. Apart from this, we also have modeled the conveyor belt and its model parameters. Simulink and Simscape Multibody provide you the option to accurately model the various parts of a complete automation system along with the dynamic movements of the system. To visualize these movements, we send the coordinates of the robot arm via UDP signals from the test system to the host PC. The Simulink model also shows the I/O blocks for SpeedCode IO75X EtherCAT I/O module that provides seamless connection between the test system and the PLC. We also have another Simulink model to receive the coordinates of the robot arm, which then sends it to a visualization application. Before we run the model, check to make sure that the test system is connected to the Simulink real-time environment, and also make sure that we configure this model precisely for the type of test system in use. This is done by going under Apps, Simulink Real-Time, and selecting the appropriate test system, which in this case is the Performance Real-Time Target Machine. Once this is done, we can now run these models together. To speed up the simulation, we will move to the part where the Simulink model is deployed and running on the target machine. For the visualization of the movement of the robot arm, we have taken the Mechanics Explorer, which is a tool from MathWorks to visualize and explore multi-body models. We can see here that the robot arm is being moved and controlled. Its model is being controlled in real time by reading all the values from SpeedCode test system from the real-time simulation. This demo shows you how hill testing helps ensure that the PLC systems are robust, reliable, and ready for real-world applications. It's time to move on to the last topic of unmanned aerial vehicles used for service applications such as for delivery and logistics support. We will focus especially on testing the UAV controllers using hardware-in-the-loop testing. As you saw previously, the SpeedGoat MathWorks environment helps you to prototype and implement the controller of a vision-guided robot, and in this case, it will be the UAV. After this, you would like to test your UAV controllers in real-world scenarios that can be simulated. To model the UAV in Simulink, you can start by using one of the guidance models for a reduced order model of the UAV, or you can either have a high-fidelity physical UAV model using Simscape Multibody. The next step would be to build real-world scenarios that can help you test the UAV controller. So let us go back to the hardware-in-the-loop testing setup, where we show you an example of a UAV package delivery. The plant modeling for the UAV is done on Simulink, and the scenario simulation is done on Unreal Engine. The controller we have used here is a PixHawk 4, and the controller software is deployed using PX4, which is an open source flight controller software for drones. Now, we will deploy the plant model of the quadcopter onto the baseline real-time test system. Here, you can see that we have used the IO397IO module to interface with the PixHawk 4 controller. Let us design a mission now. We take off at 20 degrees altitude, set up a couple of waypoints, and we can go ahead and upload the mission. We will run the full mission simulation with no noise injection. The UAV is now ready to fly. We'll go ahead and run this mission. The UAV takes off with the altitude that we have set, and immediately you can see that it starts following the waypoints that we have pre-decided. It then maneuvers itself along the waypoints and navigates from one waypoint to the next and follows it. With this, you can already see if there are any controller issues that you want to optimize, so that the full mission now is completed. Let's now run a new mission. Here, we want to simulate fault injection. In this case, would be to disable the GPS satellite links. When the UAV takes off, we see that there are all 10 satellite links available. It's going to navigate now to the first waypoint, and when we disable the GPS, we lose all our satellites. We also see an error message saying that the satellites are not available and the localization is lost. Such failures can be simulated and validated with this setup. So now, let's wrap up today's webinar. There is a single key takeaway for you today. SpeedGoat Test Systems and Simulink provide a testing solution for all aspects of controller development for robots and autonomous systems. Why is that? You can rapidly prototype control algorithms for complex robot control systems, as model-based design allows you to focus on functional design and sets you up for the implementation of your controller code. You can develop within the unified environment of Simulink and SpeedGoat, which allows you to create a digital thread that traces requirements to models, code, and tests, which helps manage the complexity. You can use performant, modular, and scalable test systems that allow you to emulate sensors and electrical signals, as well as subsystems of your robots and autonomous systems. So with this, you can then thoroughly test your controllers. Thank you for staying with us until the end of this webinar.
You want to learn more about real-time controls testing? Then find additional content linked here.